Hello everyone. My name is Nguyen Nhat, a student of Fulbright University Vietnam, and I'm thrilled to introduce my term project for the Computer Organization course. The title of my project is the Home Security System. This project began with an observation. Many homeowners face property loss due to the lack of affordable security solutions. While systems like ADT and SimpliSafe are reliable, they are often too expensive for many households. This inspired me to create a customizable, cost-effective alternative designed to provide essential security features while being accessible to a broader audience. The Home Security System is a simulated product implemented in CircuitVerse. It operates using finite-state machine principles and features key states such as disarmed, armed, home mode and away mode, triggered, and false alarm check. Throughout this project, my primary goal was to bridge the gap between theoretical knowledge and practical application. In this video, I'll walk you through the design, implementation, and demonstration of the home security system. Let's dive in. Now let's dive into the logic design of the home security system. The foundation of this system lies in a finite-state machine, or FSM, which manages the different states and transitions based on user inputs and sensor triggers. Let me explain the key states. The disarmed state is the starting point where all sensors are inactive, allowing unrestricted movement. The armed home mode state activates limited sensors, such as door and window sensors, while allowing movement inside the home. The armed away mode state enables all sensors, including motion detectors, to secure the home when unoccupied. The false alarm check state allows users to verify if a detected event is valid or a false alarm. Finally, the triggered state is activated when an intrusion is confirmed, setting off the alarm. Transitions between states are determined by specific conditions. For instance, switching from disarmed to home mode happens when the mode input is set to 01. Moving to false alarm check occurs when a sensor, such as the window sensor, is triggered. From false alarm check, the system can either return to the previous state if the alarm is invalid or move to the triggered state if validated. The system's block diagram highlights the main components: the control unit, which processes inputs and determines state transitions; the indicator module, which uses LEDs to display the active state. This logical framework ensures that the system operates efficiently with clear transitions and reliable state management. Now, let's explore how the home security system was implemented in CircuitVerse. The system was designed using digital logic gates to represent the finite-state machine and its transitions. Each state is encoded in binary logic, with transitions driven by user commands and sensor inputs. Here's how the system operates. Inputs. The system accepts binary inputs for mode selection, window sensors, motion sensors, and alarm validation. These inputs control the state transitions. State encoding. Each state is uniquely represented with a binary value. Disarmed is encoded as 000, home mode as 001, away mode as 01 Nhat, false alarm check as 0111, triggered as 100. Output indicators. The system uses 5 LEDs to display its current state. Mode LEDs. Green for disarmed, yellow for home mode, red for away mode. State LEDs, yellow for false alarm check, red for triggered. When the system transitions states, these LEDs provide a clear visual representation of the current mode and status. For example, switching from disarmed to home mode lights up the yellow mode LED. Activating a sensor while in away mode transitions the system to false alarm check, lighting the yellow state LED. If the alarm is confirmed, the system transitions to the triggered state, activating the red state LED. Now, let's see the home security system in action. The system starts in disarmed mode, represented by the green mode LED. In this state, all sensors are inactive, allowing unrestricted movement. To set this mode, ensure all switches are set to 0. Next, I'll transition the system to home mode by setting the mode input to 01. The yellow mode LED lights up, indicating that the system is now in home mode. In this state, only the window and door sensors are active, while motion sensors remain off. Now, I'll switch the system to away mode by setting the mode input to 10. The red mode LED turns on, showing that the system is fully armed. In this state, all sensors, including motion detectors, are active to secure the home when unoccupied. To simulate a sensor being triggered in away mode, I'll activate the window sensor by setting the WS input to 1. The system transitions to false alarm check, represented by the yellow state LED. This state allows the user to verify whether the detected event is valid or a false alarm. If the alarm is invalid, I set the validation input V to 0, and the system returns to away mode, as indicated by the red mode LED. If the alarm is valid, I set V to 1, and the system transitions to triggered state. In the triggered state, the red state LED lights up, indicating that the alarm has been triggered due to a confirmed intrusion. To reset the system and return to disarmed mode, I set all inputs, including mode, sensors, and validation, back to 0. The green mode LED lights up again, showing that the system is disarmed and ready for the next cycle. This project has been an enriching experience, combining theoretical concepts with practical implementation. One of the main achievements was designing an intuitive system that represents real-world security mechanisms within the limitations of CircuitVerse. The project provided valuable insights into digital logic, state encoding, and how FSMs can be applied to practical problems. However, some features, such as silent mode and maintenance mode, were excluded due to time constraints. Future enhancements could include adding these modes for greater flexibility, incorporating advanced sensors like smoke detectors, simulating real-time alerts to mimic modern security systems. In conclusion, this project has strengthened my understanding of FSM design and digital circuit implementation while bridging the gap between classroom learning and practical applications. Thank you for taking the time to watch my presentation. I hope it has provided insights into the potential of digital systems like this.